hard do you have to slap a chicken in order to cook it? Okay, so this meme has been going around like crazy on the internet. I'm not exactly sure where it started, and I don't care. What I care about is so many of you are sending this thing to me that now we have to address it. The question, wherever it originated, supposes that if kinetic energy is perfectly transformed into thermal energy, then how quickly would you have to slap a chicken in order to cook it? Okay, well, there was a physicist and numerous other internet sciencey guys like myself who responded to this with actual math, and we can do the same and actually agree with most of the approaches. But we will get to some caveats of that. So, if kinetic energy, Ke, is perfectly transformed into heat energy, Q, then we have this equation that we can set equal to each other to find the amount of energy that we need from the motion of the object in kinetic energy. So, kinetic energy equation, mass times velocity squared divided by 2, 1/2 mv squared. The heat energy equation here would be the mass of what you are trying to heat up, the specific heat, C, of what you are trying to heat up, how much energy per unit mass per Kelvin it takes to heat something up, and then the temperature difference that you want to cause. If you want to take it from frozen chick all the way up to, oh, nice tasty rotisserie, this is the temperature change that you want from 0 to whatever it is, 200 degrees Celsius. So, I went through the math of this meme, and I more or less agree with it. If you just have this equation, everything else being equal, purely physics approach, and I agree with the assumptions, then you can solve for V here. And if you do that, you get a velocity equal to around 1,600, 1,600 meters per second. Now, for some perspective, that is almost Mach 5. So, the meme says that if you were to hit a chicken with your hand, at around Mach 5, it's like Mach 4.8 or so, then your kinetic energy will go into heat energy in the chicken and cook it. We're not done though, because this is from a purely physics approach. If kinetic energy perfectly transfers into the chicken, then this speed makes sense. However, this is not a purely physics question. Let's say you have a chicken and you hit it with your hand. What is actually going on? Well, your hand is deforming the tissue of the chicken. That kinetic energy of your hand causes deformation, which does cause heat. The kinetic energy is transformed into heat because energy is neither created or destroyed. It just transforms into other forms. Anyway, it transforms into heat energy inside of the chicken, but there's also the sound of the slap. That's the sound that a chicken slap makes. And there's also acceleration. You can accelerate the chicken as you hit it. So the energy is divided among these different modes from the kinetic energy, which is to say that it is not 100% efficient transfer. Not 100% of kinetic energy all goes purely and exactly into heat. This would in effect push the velocity that you'd have to hit the chicken at up, or at least a little bit up, some percentage up, 10%, 20, 30, 40, whatever it is, whatever the efficiency rating is. This would push the speed up. So now you have to hit a chicken at Mach 5 or more. What would really happen if your hand hit something at Mach 5? What happens when anything hits something at Mach 5? In reality, if you hit a chicken at this speed, it would be obliterated. Absolutely obliterated. And let me give you a comparison in terms of energy. If we stay within an order of magnitude of the energy values here, purely physics approach, then it's equivalent to say that if I put myself on a rocket sled going 650 miles per hour with my hand outstretched like this, and then I went, oh, at 650 miles per hour, and I was launched by this rocket sled, and I hit the chicken with my outstretched hand, it would be almost exactly the same amount of energy, using my weight, using the velocity of the rocket sled, almost the same amount of energy. And then, therefore, it should heat up the chicken until it's cooked, right? No. What do you think would happen to your hand and your body if a rocket sled carrying your body hit a chicken? Well, if you've ever seen the episodes of Mythbusters that use the rocket sled or looked up rocket sleds in your spare time, you super nerds, you know that something with this mass going that speed can not only obliterate a target, it can destroy the very thick concrete wall and berm made out of soil behind it. This is a lot of energy. And all of that energy going into a chicken would act to destroy it completely before there was enough time for enough heat to transfer in perfectly with 100% efficiency to cook it like a nice chicken dinner. So, how hard do you have to slap a chicken in order to cook it? You can't. It's the same reason why, if you ever read XKCD, Randall Monroe goes through this, it's the same reason why you can't heat up a cup of tea hot enough to steep your tea just by stirring it. You'd have to stir it so quickly and so forcefully that it would act to destroy the cup and slosh the water everywhere. This is more or less the same scenario. The force you'd have to hit the chicken with and the velocity you'd have to hit it with would destroy it before you cook it. Can you slap a chicken hard enough to cook it? No. But from a purely physics perspective, you can set up an equation and get a value and then get lots and lots of fake internet points. Hello. That was a long one. Hello and welcome to another edition of Because Science Live, the live show on this channel where I take all of your comments, questions, and corrections and try to address them to the best of my ability. Look, whoa. I'm not an expert, I'm not a working scientist, but I do know a little bit about a lot of sciencey and pop culture-y things, so if I cannot give you an exact answer, I will punt on it. That's a sports reference for all you nerds out there. And if I don't know something, I will say I don't know something, but hopefully I can be entertaining and interesting for you all to the best of my ability. Nate!
Yeah, what's up, Kyle?
Why are you talking like that? Is it because we're on YouTube?
Yeah, it's YouTube.
Sure is,
It's the
pal.
TV of the future.
Yeah. What do we got?
From Thomas B.
Man, he's sounding so much cooler already.
Since tardigrades are nearly indestructible and can survive in space, could we send them to other planets to start colonizing those planets with life? Would we ever want to?
That's interesting. So tardigrades, interesting you bring this up because I was kind of researching it. Tardigrades are arguably the hardiest animals that we've ever discovered. Tardigrades have a number of ridiculous statistics to their name. Just a few of them. It's going to sound like I know this immediately, but it's only because I've been looking it up recently. Tardigrades can survive negative sub-zero temperatures, Celsius-wise, like negative 20 degrees Celsius for, 30 years? And be fine, be revived afterwards. They can famously, of course, survive the vacuum of space for 10 days. An experiment in 2007 discovered that. And they can also survive a higher dose of radiation than any animal that we know of. That includes cockroaches and us, of course. So tardigrades are incredibly durable animals. And they have this durability because they do something to their bodies when they encounter a harsh environment. Tardigrades are not considered what are called extremophiles. Extremophiles are able to live and thrive in extreme environments. But what tardigrades do, or water bears or moth piglets if you're fancy, which I am, what moss piglets do is they change their bodies so that they can endure an environment until that environment gets better, which is slightly different. So what they do is they draw in their heads and their legs so that they look like a little ball of water bear, and they draw them in and they slow their metabolism way down, like 0.01%, all the way down, almost. So they're still not technically dead. Then they lose almost all of their water. And in this phase, they become what's called a ton, T-U-N. And in this phase, they are able to survive harsh conditions, radiation, pressure differentials, either high, very, very high, or very, very low, like in space, temperature differentials. They're amazingly hardy in this state. Now, I say all that because if a tardigrade is to survive on something like Mars, it will probably put itself into a ton-like state, which means that it's not moving around, it's not replicating, it's not advancing its genome within its population, it is not doing little jobs that we could give it. I don't know what that would be. Here, move this moss over there. Maybe Elon Musk will do that. But all this is to say that a tardigrade could probably withstand, at least for a little while, more than we could, the environment of Mars, but it's not going to be moving around and being very active and being like it's living on Mars. It's more enduring Mars. And so using tardigrades as some kind of precursor to human life, I don't think would be very useful. What would be more useful is landing a crap load of machines and robots on the surface to build habitats before we even get to Mars. They would be able to endure these temperatures, these pressures, the lack of oxygen, all this stuff much better than a tardigrade. Even though a tardigrade might live, it's not going to be around and working. So I would defer to robots and not water bears for the colonization of Mars. Also, what do you think that the tardigrades are going to do? They're microscopic. You'd need a lot of How many tardigrades would you need to move? See, I'm getting further off track. Good question, though. What's next?
From Sam Average Man.
Did it have more than one A in Sam? Is that why you said
it? It had 2 and it's uppercase.
Sorry,
fancy.
my bad. Surface to air missile.
How are sapphires, rubies, and other gemstones formed?
I don't know. I'm gonna guess that it's okay. So sapphires, rubies, diamonds. These are minerals in a crystalline form, meaning that when they're not very amorphous. So the difference between amorphous and crystalline is that in an amorphous solid, you have particles all over the place, jumbled, not in any real arrangement. In something that's more crystalline, you would have a nice lattice-like structure that all of the atoms and molecules were following. I know perspective. We're following. So this is a more crystalline structure. So when you have these beautiful gems, what you're looking at is a repeating crystalline structure that is more or less pure, and that's why diamond jewelers talk about. That's redundant. That's why jewelers talk about purity and such. And when you have impurities, you can change the color of diamonds. Anyway, so you have crystalline structure. Now, to create these kind of crystalline structures, as far as I know, and I may be incorrect, in the case of gemstones, you need what's needed in a lot of formations of rocks. You need incredibly high temperature and incredibly high pressure. I do not know off the top of my head what sapphires and rubies are made out of atomically, but I would guess that how to make them is that you get enough of the atoms and molecules that make up that material in the right place and subject it to the right environmental pressures and temperatures such that they start forming these crystalline structures, and then they are thrust up from the earth by some geologic event, some volcano, something like that, and then they make their way to the surface and we find them and then we assign some commercial value to them because we, as primates fascinated by shiny things on a pale blue dot floating in the middle of space, in the middle of nothingness, we find value in these things and we say, ooh, I got one of these and you don't got one of these, so I have more commercial value than you. Then we use these as forms of currency in some instances, then we use them to barter and trade, and then we... What's next? I was starting to get weirded out.
From Spartan 117.
Don't laugh at me, Nate. I was
starting to.
I was going to start a manifesto, I felt like. Anyway, some crystalline structure pressurized in the earth and we find them later.
From Spartan 117.
John? Hey, dude. One time I calculated if you could survive a fall from space. How you doing? Find Cortana? I haven't played the rest of the games.
How long until the sun dies?
I feel bad because I don't know the exact value on this, but the time frame that we have is on the order of billions of years. Now, there's two different numbers that you will usually see stated for the lifetime of the sun. One is much less, 5 billion, and one is much more. I forget which one that is, what value that is. But in around 5 billion years, the sun will go into another phase of its life. And that phase of its life is the red giant phase. And in that phase, the sun will expand and expand greatly. It will expand so much that it will consume us and consume a few of the inner planets in its radius, I think. Or it will just get close. I'm not an astrophysicist. But it will expand such that it will get so hot, or it will consume the Earth. It will get so hot that Earth will be... Oh, no, wait. No, I'm right. Yeah. Red giant phase, Earth is obliterated. Everything on the surface dies. 5 billion years. A few more billion years from that, the sun will start to run out of its hydrogen and helium fuel. It will start fusing heavier and heavier and heavier elements together until it hits iron. At that point, it will start the amount of energy that it will take to fuse elements together in its core is no longer enough to provide enough thermal energy to fight the inward collapse of gravity from its mass, and then the sun will die and explode. A few billion years. But and I keep, when we talk about doomsday scenarios and stuff like that, yes, we are going to die for sure if we're still on Earth in a few billion years, like 5 billion years. But the time frame on humanity right now, with especially with things with climate change and resources being as they were, and inequality and stuff like that. Anyway, more so climate change. Because of that, the time frame on real, enjoyable human life is not a few billion years. It's a few hundred. We really need to get our crap together. Get it all, I don't care what you do with it. Get it all in a bag, put it in a bag, get it together. Get your crap together. Put it in a crap museum. I don't care. But get your crap together. Get it together. Yeah, I watch Rick and Morty. What's next?
From Tsar TV.
Tsar TV, the only TV where you too can watch all the greatest Russian military exercises.
In episodes about Star-Lord and Leia, you
Yes.
cover how sci-fi handles effects of space on human bodies.
Yes.
Focusing on effects of temperature and pressure. Is radiation a factor?
Yeah, wow. You're asking me a bunch of questions that I have recently looked up. So I will say that recently Hollywood has been pretty good about what happens to a humanoid body in space, even though people in Star Wars aren't technically humans, are they? It's weird to think about. But they're humans, but they're not humans. So if Princess Leia or Star-Lord is in space, I think in both of those scenes, what you do see is frost starting to cover their face. And this is accurate. In space, with no ambient pressure, the vapor pressure of the moisture in your tissues and the saliva in your mouth and stuff like that, the vapor pressure of that liquid is higher than the ambient pressure, so it will immediately boil. And when it boils off, heat will be removed so quickly that you will get a layer of frost on your moist tissues, your moist towelettes, if you will. So that is accurate. What Hollywood does not really show, and I'm fine with this. I'm fine with when Hollywood doesn't always show every single possible accurate outcome of something, because you still have to tell a story, and you don't want it to take 5 minutes just to explain something for no reason. Anyway, that's pretty good in Hollywood. But what Hollywood is not showing is loss of consciousness within a few seconds, like 15 seconds or less, 9 to 15 seconds, because when you're in space, all of the air in your lungs will and in your blood will exchange itself because of how gas exchange works in your lungs, and your blood will become very rapidly deoxygenated. All of that will make its way to your brain, and you will lose consciousness within seconds, and you will die, or you will be unable to be revived, as far as we know from testing that we've done on animals and primates and chimpanzees, within about 90 seconds. In most movies, TV shows, 90 seconds is valuable screen time. So you do not have, you have to jump cut, you have to advance time, things take too long, too short. So if Hollywood wanted to be more accurate, they would have shown Star-Lord, for example, when he's trying to save Gamora in space. He would have passed out very quickly after taking his mask off, and he wouldn't have active consciousness. Although I think when we went through the episode, it's pretty close, so I'll give it to him. And if they wanted to be even more accurate, aside from losing consciousness very quickly, they could show the human body slightly bloating as tissues would expand because of the boiling fluids and boiling blood inside of you. You would expand a little bit. But aside from that, you're not going to explode. Blood isn't going to erupt out of your face like in Event Horizon. Miller! That's not going to happen. So Hollywood is quickly becoming more and more accurate to what would actually happen to a human body in space. And that is not very much. I mean, you would die pretty quick, but it's not it's not as visual as some horror movies and space movies make it out to be. You would, though, get horrible sunburn within a few seconds because without an atmosphere to protect you from ultraviolet rays from stars like our sun, it would slam into your skin and you'd get sunburn really, really quick. And it would be the worst sunburn of your life. But that's fine because your life is rapidly coming to an end in that scenario if you're unprotected. What's next?
From Roman Yunker.
Ho ho!
I love your show.
Thank you.
Any idea what the slowest moving object in space is?
What's the slowest moving object in space? Well, I have two answers. One answer is 0. 0 meters per second. Whatever's moving that speed or velocity, wherever it's pointed. I say that with a caveat. Relative to what? Everything in space is falling towards something else. Gravity affects everything everywhere. No matter how far away you are from something, mathematically you still have some gravitational force on you by that something. Even if you're a million miles away, billions of miles away, trillions of miles away, the math doesn't care. It may be effectively 0, like affecting you almost nothing, but it's still there. The moon and the other planets, as astrologers will like to say, do have some gravitational effect on you, but that gravitational effect is so small that it's not likely to do anything to your biology. So they're right that they do have some gravitational effect, but they're wrong in that that effect has anything to do with your life or your destiny or what have you. Anyway, the slowest moving thing in space is probably impossible to say because you'd have to choose a relative point. We'd all have to agree on a relative point because everything is always moving. Everything is always falling towards something else. If you pick a different position, its relative velocity will change. So like we went through in the teleportation episode, I am not moving relative to the Earth's surface right now, but the Earth's surface is spinning at 1,000 miles per hour near the equator. So I'm going 0 if you choose the reference point of the surface of the planet, or wherever the surface of the planet is. But if you remove that point and you look outwards and you look at me, I am now moving 1,000 miles per hour in a circular motion. So slowest moving thing in space is would only be calculable if we all chose one reference point that we all agreed on. So, like my boy Einstein said, it's relative. What's next?
From Randy B.
I think he said that at one point. I think he went like this. It's relative.
That's pretty accurate.
Yeah, thank you.
From Randy B.
Randy B.
If you could be any Mortal Kombat character, who would it be?
I've always had a fondness for Scorpion. I've always loved the get over here kind of thing. Sub-Zero is very cool. But do you know who I was in Mortal Kombat? I was always Noob Saibot. Because not only did he look cool, he had easy special moves, and he had a 4-move combo that was just hitting square 4 times on the PlayStation 2 or 1 controller. And that was an immediate combo, and it was very easy to do, which is why they called it Noob Saibot. That's not true. It's called Noob Saibot because those are the 2 last names of the guys who created him. One, Ed Boon, and the other, whatever, that reversed is. But Ed Boon, and I asked him, he co-created Mortal Kombat, and I said, is it because noobs have an easy time with it? And he said, no. But I said, can that be canon now, though? And he said, sure. So, it's officially correct. The best kind of correct, technically.
From Allison Ross.
Hello, Allison.
How big does something have to be to have its own gravity?
Well, we kind of already got at this a little bit. As long as something has mass, it can have a gravitational effect on something else. Do I take the chance? Sure you do. Yeah, sure I do. So if something has, so the force of gravity on something is going to equal the Newton's gravitational constant g here, multiplied by the mass of the one thing times the mass of the other thing, divided by the radius or distance between them squared. Now, you can see here, if you are M1, as long as you have mass, there is some force between you and another thing. It looks like my face is being smashed by a rocket sled. I kind of like it. There is some force between you and that other thing. So the smallest possible thing that doesn't have a gravitational effect on something else would be something with no mass. And even that gets complicated because something like a photon that has no mass, it still has momentum, and so it can be affected by gravitational fields. There's a really, really cool thing called a photon sphere. And the gravity around a black hole is so strong that it can curve photons in their path, or kind of doing like a what's that band called? Guns N' Roses kind of thing. So a photon does a Guns N' Roses kind of thing around the photon sphere of a black hole, and it gets trapped there. And there's just light trapped in a sphere around a black hole doing a Guns N' Roses thing, as we said previously, which is now the correct term. So if you consider the photon as well and how it can be affected by gravity, everything can be affected by gravity. Even dark matter has a gravitational influence. That's how we know dark matter is there. Dark matter doesn't seem to interact with anything else that's regular matter. That's why we call it dark, and we can't see it, with our eyes, of course. But dark matter has a gravitational influence on the galaxies that it's in, their spin. That's how one of the ways we detected that it's there. We said, this galaxy is spinning way too fast. There's not enough mass to make it spin this fast. There must be some dark matter there that is accounting for this rotational velocity. So as long as you have mass, Allison, you have some gravity, which means all of us affect each other all the time.
Last question.
Oh, thank you. I didn't know what was happening.
Thought you were pausing for effect.
I was pausing for effect, and then effect is over.
From Jim Beck, this is a maintain question.
Wonder why.
If you use argan oil on your hair, would you try straightening it with a heated hair straightener?
Ooh, I'm not. That's next level maintain, brother. I don't know if you can straighten your hair with oil in it. Maybe we should try that. Look. Here's the thing. If you want to straighten your hair, then apply the oil. The oil is better for sheen, reducing frizz, making it look shiny, like you just, like it's healthy and shiny, got a nice sheen, got a nice coat on you. Ooh, yeah. So apply it after you take a shower. Your hair's damp, and then if you want to blow dry it a little bit, then apply just a little dab of argan oil. This is a little dab, less than a half a pea is worth. Dab it up. Rub it, then put it on your hair. And you too can maintain. Thank you. Wow, what a question to end on. Thank you so much for watching this edition of Because Science Live. I hope you all enjoyed our little excursion into chicken physics, or chick-six, if you will. If you want to clip out that beginning section and send it to all your friends who keep asking you about how to slap a chicken, I would very much appreciate it. And thank you so much for joining me for everything that we're doing on this channel this week. Of course, next week we have another vlog, we have another live stream, we have another main episode, and on top of all of that, we have the first behind-the-scenes episode for Mortal Kombat going out on Monday. Yeah, that's right. If you haven't heard, we have partnered with Warner Brothers and NetherRealm Studios to do the science of Mortal Kombat, a 6-episode series with 6 behind-the-scenes episodes that is airing from now for the next 11 weeks. The first episode, where we shatter a head maybe with physics and a very, very strong man, is now up on the channel. I'm very proud of it. It looks so much higher quality than a lot of the stuff that I try to do here. So please go check it out. Let me know what you think. Have a wonderful rest of your weekend. I really mean that, because this connection, force, feeling, this is all we got.